In this video, we're going to look at resistors and basic circuits, and at the end we'll look at how to combine resistors in series and parallel, similar to how we did capacitors previously. Now that we have seen how applying a voltage causes a current and their relationship given by Ohm's law, we can imagine that we may want to limit the current in circuits. We'll give a definite reason for this later, but you probably know intuitively that conducting large amounts of electricity or electric current can be bad. Ohm's law tells us that we can do this by increasing the resistance of our circuit. And we saw before, an object's resistance depends on the material and its shape. We have specific circuit components whose job is to provide resistance to a circuit, and we call them resistors. In a circuit diagram, we draw resistors with a little zigzag symbol. In actual circuits, you may see them look like this. Here, the material between the two wires is designed to have a very specific resistance. The color bands correspond to the resistance value and can be read using a chart. Resistors are ohmic, meaning they follow Ohm's law, which says the current increases linearly with the applied voltage. Plotting the current as a function of the applied voltage, the resistance is given by 1 over the slope. Not all materials are ohmic. Some are non-ohmic, meaning the current may rapidly increase at a faster rate as voltage is applied. Or maybe there's no current until a threshold voltage is reached, and then the current shoots up. The linear behavior of ohmic resistors allows us to have easy control and predict their behavior, and so we'll only look at resistors that follow Ohm's law. There are many practical uses for non-ohmic materials and things that don't follow Ohm's law, such as diodes, but we won't look at those here. Metal wires that we use to connect elements of a circuit have low resistance. So to simplify things, we want to imagine our wires are ideal, meaning they have no resistance or don't contribute significantly to the resistance of the circuit. Then we have resistors made of insulating materials, which are poor conductors. An ideal insulator would have an infinite resistance, meaning it would not allow any charge to flow at all. Our resistors will not be made of ideal insulators, but we can design our resistors to have specific values that allow us to precisely control the resistance of our circuit. Now let's connect our resistor to a battery. The battery will raise the potential energy of charges, and these charges will move through the wire to a lower potential. This means there will be a current from the positive terminal through the resistor to the negative terminal of the battery. Since we'll assume we have ideal wires, the potential does not change moving across the wire. The potential must decrease from the positive terminal to the negative terminal, so all of the voltage must drop across the resistor. This leaves the wire on the left at equal potential with the positive terminal, and the wire on the right at an equal potential with the negative terminal. And we'll imagine the potential decreases linearly from the positive side of the resistor to the negative side, though the details of what happens inside the resistor won't matter much for our analysis of the circuit. Before we continue looking at circuits, let's look at the symbols for basic circuit components. We've already seen a few of these. We will draw a battery or voltage source with 4 parallel lines that alternate in size. The positive terminal, or the side of the battery at higher potential, will be next to the larger line and the lower potential by the shorter side. Wires will be segments of straight lines that we use to connect other circuit components. The wire can change directions and will be considered the same wire until it reaches a circuit component or it splits. When a wire splits or 2 wires come together, we call this intersection a junction. Even if a wire splits or 2 wires come together and become one, because they are all ideal, they will still all be at the same potential. However, the current or charge flowing through the wires may be different. If a wire splits, some of the current will go through one branch and the rest through the other branch. If 2 wires are bringing current together, it will all leave in the wire where they meet. Because of this difference in current, we will differentiate between the wires coming into or leaving a junction. We've already seen capacitors that are represented by a single pair of parallel lines. This is why we use 2 pairs of parallel lines for the battery, to differentiate a battery, which is a voltage source, from a capacitor, which passively carries a voltage, while it is charged or connected to a voltage source. Then we have a resistor, which we just looked at. Similar to a resistor is a light bulb. We draw a light bulb as a circle with a bent wire in the middle. A light bulb can be thought of as a resistor that lights up when current passes through it. Finally, we have a switch that we can represent with a gap or a break in the circuit. This physical gap prevents current from flowing, and closing the switch will allow current to flow. Now let's look again at the circuit with a resistor connected to a battery. In analyzing a circuit, we want to be able to find the current through and the voltage across each component in the circuit. To do this analysis, we will break our circuit into loops. Here we only have one loop, but you can imagine more complicated circuits where our wires split at junctions, forming other possible loops. We analyze these loops in our circuit one at a time. Once we choose a loop we want to analyze, which in our case is the whole circuit, we must choose a starting point. Then, from this starting point, we choose the direction in which we want to move around the loop, so clockwise or counterclockwise. For simple circuits, I like to start at a point just before the negative terminal of a battery. Then, I like to move in the direction of the current, which in this case, that would be counterclockwise. Then we apply Kirchhoff's voltage law or loop law. This says that the total potential difference around any closed loop is zero. As we move around the circuit, the potential will increase or decrease as we cross circuit components. But the potential value at any one point should not change. So choose a point and then move around the circuit and return back to that point. We should always arrive at the same value. Let's imagine this a little differently. I want to imagine the potential value as elevation. Since batteries are voltage sources and increase the potential energy of charges, the positive terminal of the battery is at a higher potential than the negative terminal. Wires between two components should be horizontal, since every point in our ideal wires are at the same potential. Since our potential must decrease to get back to the low potential on the negative terminal of the battery, it decreases across the resistor, which connects the wires on either side of our battery. We can think of our battery as an escalator that takes our charges to a higher elevation or a higher potential, and the resistor acts kind of like a bumpy slide. The charges go down to a lower potential. Now let's imagine we choose our starting point from before. We said that if we go around a loop and return to this point, we should be at the same potential, which in this case corresponds to the same height. We could imagine riding up the escalator of the battery and then down the bumpy slide. But notice our statements only work if we go around the loop in the same direction we expect the current to move. Mathematically, there is nothing to stop us from going the other way. We could climb the slide to a higher potential and then run down the escalator to a low potential and return to our same point. This means we gained potential across the resistor and lost potential across the battery. But the total change in potential was still zero, regardless of which way we went. So Kirchhoff's loop law still holds, even though this isn't physically what may happen in the circuit. Now you may ask, why would we ever choose to go around a loop in the opposite direction of current, or the opposite direction charges are actually moving? The answer is that not all circuits are this simple, and sometimes we cannot avoid going against the current in some branch of the circuit. We also may have multiple batteries, and we may not be exactly sure which direction the current is going to flow. So we need to know how to analyze the circuit in any case in order to figure out what's actually happening. So in general, we can look at when the potential difference is positive or negative for batteries and resistors. Batteries bring charges from low potential to high potential, or negative to positive. Don't get confused here, because in the rest of the circuit, current flows from positive to negative. Batteries supply the source voltage, so they act against what charges want to do naturally, which is move to a lower potential. If we choose to go around our loop in this same direction, we will see an increase in voltage across the battery equal to the battery's EMF, assuming it is ideal. And if we go the opposite direction across the battery, from positive to negative, we will lose voltage. Now for resistors. Resistors are passive elements that just sit in our circuit. When current flows through a resistor, it is going from high potential to low potential, and the resistor just happens to be in the way. If our loop goes against the current, we will gain voltage across the resistor. If we go with the current, we are going in the direction charges will flow naturally, which is to a lower potential, so we lose voltage. Now let's look at energy and power. Batteries increase the potential energy of charges by raising them to a higher potential. This change in potential energy we already know to be the charge times the voltage, which in this case of an ideal battery is the EMF of the battery. Since the battery is constantly increasing the potential energy of charges in a circuit while the current is flowing, we may want to look at the rate at which energy is transferred from the battery to the charges in the circuit. This is the power and is equal to the change in energy over the change in time. We can also write this as the instantaneous power using derivatives. Since the EMF of the battery is constant, we get the power is equal to the current times the EMF of the battery. This is the power delivered by the battery to the circuit. So what about the resistors? When charges travel through a resistor, they move to a lower potential and lose potential energy. But this energy must go somewhere. We treat the wires as ideal when there is no resistance, so we imagine the charges are moving through the wire without colliding with atoms or other charges. But the resistor does have resistance, so the moving charges are experiencing collisions as they travel across the resistor. During these collisions, the charges transfer energy to the atoms in the resistor, increasing its thermal energy, or the energy associated with the vibrations of the atoms in the material. This increase in thermal energy is equal to the change in potential energy, or the charge times the potential difference across the resistor. If we look at the rate at which this energy is transferred in time, we get the same equation as for the battery, but now we have the voltage across the resistor instead of the EMF of the battery. In the case of a single ideal battery and a single resistor, these voltages are the same. This won't be the case in general. We can also rearrange Ohm's law and substitute it into this equation for the power to get other ways of finding the power dissipated by a resistor. So the power is either given by the current through a resistor times the voltage drop across that resistor, or the current through that resistor squared times its resistance, or finally the voltage drop across the resistor squared divided by its resistance. Each resistor in a circuit may have different current, voltage, and resistance values, so all of these are for a single resistor, and each formula is equally good for finding the power. I do want to focus on two of these formulas really quick, starting with the current squared times the resistance. This formula doesn't have the voltage across the resistor, which may change depending on the source voltage of the battery. This tells us the power, or rate of thermal energy transferred, is proportional to the current squared. Thermal energy is another way of saying heat, and this means if we double the current through a resistor or some other object that has resistance, the rate of heat dissipation is quadrupled. This is one of the main reasons we said we want to use resistors to limit current in circuits, because they get hot and can cause unwanted fires. The circuit breaker in your house is designed to detect when current has gone above some threshold. When this happens, a mechanical switch, usually made with a magnet, opens the circuit and prevents current from flowing. This helps prevent your house from catching on fire due to too much heat being dissipated from a high current. We'll be able to see exactly how the circuit breaker opens the circuit at a specific current value when we look at magnetism. We can also look at another equation to see why we have high voltage power lines. We want to provide power or energy at a particular rate to homes and businesses. Because energy is conserved, we can only provide the power that we generate, so we don't want to lose any. The higher the current, the more energy that we lose to heat and cannot use to power our homes and devices. So looking at the formula current times voltage, we can keep the power the same by lowering the current, but increasing the voltage by the same factor. This means we're able to transmit large amounts of power over long distances with little loss because the voltage is high and the current is kept low. This is why we cannot ignore energy and power of circuit elements and other devices. They play a large role in our everyday lives. So now that we have a good reason for having resistance to limit our current, let's see how to achieve different resistance values. In circuits, typically resistors, capacitors, and other circuit elements are only manufactured at standard values across a wide range. It would be impractical to make a resistor for every possible resistance value imaginable. Instead, we take these standard resistance values and we combine them to give us the resistance that we need. We also may need different amounts of current and voltage at different parts of our circuit, so we may need multiple resistors anyway. We'll begin by looking at the effect of combining resistors in series. Doing this means the current must pass through both resistors. It cannot go through one without going through the other. We can also draw an equivalent circuit, where we imagine replacing these resistors with a single resistor, and this circuit is to behave exactly like our series circuit. We'll call the resistance of this single resistor the equivalent resistance. First, notice that there is only one route from the positive terminal of the battery to the negative terminal. This means in passing through both resistors, we must drop the full voltage of the battery. This voltage must also be dropped across the single equivalent resistor. We actually don't even need to look at the terminals of the battery at all. If we take the same 2 points, call them A and B, on the series circuit, the potential difference between A and B should be the same if we swap these resistors for our equivalent resistor. The potential at A and the potential at B should not depend on the resistor between them. The total potential difference between A and B should be equal to the voltage across the first resistor plus the voltage across the second resistor. Each of these voltages will equal the current times their respective resistance values. There are no junctions, so by conservation of charge, the same current will pass through both resistors. Now we can write the equivalent resistance as the voltage from A to B divided by the current, just using Ohm's law. Plugging in the total voltage and substituting the resistances, we see the current will cancel, and the equivalent resistance is just equal to the sum of the individual resistances for resistors in series. Now we'll look at resistors in parallel. This means current may pass through one resistor or the other. The current will split at a junction where some of it passes through the top resistor and the rest passes through the bottom resistor. Again, we'll compare this to an equivalent circuit where we've replaced the resistors in parallel with a single equivalent resistor. If we again label points A and B on either side, we see there are two paths from A to B. The resistors in between should not affect the potential values at A and B, and regardless of which way you go, you should arrive at the same potential. Using our elevation analogy, if one charge traveled through the top resistor and another charge traveled through the bottom resistor, they must end up at the same height at point B. Otherwise, B would have two different values, which would not make sense. So we get the voltage from A to B is equal to the voltage across the top resistor and equal to the voltage across the bottom resistor. The currents, however, will not be the same. The charges moving from the positive terminal of the battery will split up, with some going through the top branch and the rest going through the bottom branch. But the total amount of charge must remain the same. So the current out of the battery going into the junction we'll call I, and this must equal the sum of the currents I1 and I2 leaving the junction going through the resistors. This charge will meet back up at the junction past the resistors, giving a total current of I going back to the battery. Just as we did with capacitors, I'm going to write 1 over the equivalent resistance for this case. This is equal to the current through the equivalent resistor, which is the same current coming out of the battery, divided by the potential difference from A to B. Writing this current as the sum of currents I1 and I2 through each resistor, we can break this sum into parts. This gives us 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2. We wrote this in this way so that we could separate these terms like this, which we couldn't do if we just started with Req and had the sum of the currents in the denominator. As with capacitors, this is not the same as simply adding the resistance values. We also must remember to invert our result after adding the reciprocals of our resistances in order to solve for the equivalent resistance. If we forget to invert after adding, we will not get the correct answer. You may also notice that capacitors in series add like resistors in parallel, and capacitors in parallel add like resistors in series. If you notice this, you only need to remember one of the four, and then you can figure out the rest, though you can always just look up the formulas if you need to. As with capacitors, adding resistors in one way will always result in a larger overall resistance, and adding the other way with the reciprocals will always lead to a smaller effective resistance. This allows us to fine-tune the resistance of our circuit to a very specific value. Now we are ready to begin looking at more complicated circuits, and then we will combine capacitors and resistors into a single circuit and see how they behave. So that's it for this video, and I'll see you in the next one.